let's say I ask you to rank the size which is the ionic or atomic radii of the following. So if I give you some ions, just make something up here. Okay, so if I ask you to rank these, so it doesn't really matter what the charge is or whether it even has a charge or not, you're still looking at the same factors that affect the size. Right, so the factors that affect size are, the main one is, good, shielding. Right, and that has to do with how many, mainly it has to do with, well, really it has to do with the overall number of electrons. Right, the more electrons, the more their negative charges repel one another, and the more they force each other away from the nucleus. But we know that the majority of the shielding comes from the core electrons, because they're always between the valence electrons and the nucleus. And since the size is the size of the atoms, depending upon how far away the valence electrons are from the nucleus, it's the core electrons that really repel and shield the valence electrons between all their negative charges, preventing the valence electrons from really getting close to the nucleus. So when we're looking at shielding, the first thing we look at is the number of core electrons, and that may be enough to help us figure out, exactly which one of these should be larger and which should be smaller. If there's significant differences here, then we can just rank them based on that. But the second factor is the number of protons. And so we said if the shielding is similar, then we look to the number of protons. The more protons there are, the smaller the atom, because more positive charge to attract the electrons closer. So if we want to look at the core electrons, we would have to analyze these. So if it has a charge, we have to adjust the number of electrons based on that charge. So if it has a positive charge, we would look at where the valence electrons are and take one of the valence electrons out. So ZR, zirconium, is here. Element 40, it has a full fourth energy level up to Kr. Then it has a 5s2. And this is the 4d, so it has 2 electrons in the 4d. So it has 5s2, 4d2. Which of those electrons is going to be removed if I give it a positive charge? Right, the 5s, because that's the valence level. So it still has the n equals 4 as its core. And it has 1 electron in the 5s. Really, that 1 electron's distance from the nucleus is going to be the main thing that determines the size of that atom. And since that 1 5s electron is shielded by all the electrons in the first 4 energy levels, so that repulsion causes that 1 electron to get kind of far away from the nucleus. So Se minus, so selenium normally has 34 electrons, put 1 more in to give it an extra negative charge. So we'll have 35 now. So its outer electrons are in the 4p. So that means that n equals 3 is its core level. So in the beyond n equals 3, it has 4s2, 4p7. Sorry. Not 7. (4p) 5. 7 valence electrons, but only 5 of them are in the 4p because 2 are in the 4s. So Sb, antimony is 51. It has a full 4th energy level, and then it has the 5s2, then it has the 4d10, and then it has the 5p3. So n equals 4 is its core level. And those are its valence electrons. Ar minus, now normally Ar is really stable, so giving it a negative charge is not very likely to happen, but if we were dealing with that, we would have to put 1 electron more into the argon than it would normally have. So it would become 19 valence electrons. With 19 valence electrons, it has its full 3 energy levels that it normally has, plus 1 in the 4th energy level, so its core now is all 3 of the 1st energy levels. Now it has 1 electron in the 4th level. And then cadmium 2 plus. So normally cadmium has, just like zirconium, a full 4th energy level to Kr, and then it has a 5s2, and then a 4d10. And if we lose 2 electrons, they're the 5s electrons, right? So the valence electrons, the ones that have the highest principal energy level, they're going to be lost first. So this has no 5s, and that means it has the 4s, 4p, and 4d still. It doesn't have any electrons in the 5th energy level, so its valence electrons are now in the 4th energy level. So we can start to rank from smallest to largest. So the 2 that should be the largest should be the ZR and the SB, right? Because they have more layers of core electrons. They have 4 layers of core electrons, whereas the other 3 have 3 layers of core electrons. So between the 2 of them, since they have similar amounts of shielding here, what I need to know is if they have similar amounts of shielding, which has more protons. And so selenium always has 34 protons, argon always has 18. And that's a lot more protons for selenium, so that should be the smallest. So using these 2 factors is not always going to give us, necessarily the correct answer. There are exceptions to this logic. If I have 2 atoms that have significantly different amounts of shielding, but one has way more protons than the other, then maybe the number of protons is a bigger factor than the shielding. So, this is the order we go in, and this is what I expect you to do on the test. Just want you to know that, there could be exceptions. So as long as you can use these 2 factors in this order in a reasonable way and explain how you're getting this ranking, that's the important thing, though. That's what you'll get credit for. So then the other 3 have their valence electrons. Oh, I left this one out, didn't I? The cadmium 2 plus. This one's a little bit tricky because it has 3 layers of core electrons, but it does still have a lot more n equals 4 electrons than, say, the argon or the selenium. So based on our ranking, going with shielding first and looking at the number of core electrons as the main thing that affects the shielding, you'd probably put the cadmium here as the smallest. It has the same number of core electrons as the argon and the selenium. I guess I just overlooked that initially when I was looking at the core electrons there. So we might find that the cadmium 2+ is actually a little larger than them, maybe just because it does have so many extra electrons in the 4th energy level, but this is a reasonable ranking based on the major factors. Again, your answer, the points you get on this question is going to be much more associated with, how you explain your answer and that you've used the factors that affect size the way that we talked about using them. So then the last two here, let me fix this. I skipped over the cadmium, so I want to give that a full analysis. The cadmium 2+ has 48 positive charge, right? So I kind of overlooked mentioning that. And that's important. So as we said, since they have their valence electrons, or the same number of core electrons, they have similar amounts of shielding. Even though all these extra valence electrons will cause cadmium a bit more shielding than selenium, which will have a bit more shielding than argon, they should have similar degrees of shielding because they have the same number of core electrons, n equals 1 through n equals 3. So then we look to see which has more protons. So the 48 protons versus 34 versus 18, that's what allows us to then make the difference between these ions if they have similar amounts of core electrons. So then between the zirconium plus and the antimony, they also have similar amounts of shielding because they have the same number of core electrons. So we have to use their protons to look for the difference. So zirconium has 40 protons and antimony has 51. So the antimony should be smaller because it has more positive charge to attract a roughly similar amount of electrons closer to the nucleus.